I'm Ed Krawczyk, and I'm the lead instructor for embedded security and hardware hacking. In today's distributed computing environment, the ability to update software after it has been shipped to the user is critical. Medical devices, consumer electronics, and self-driving cars are only a few examples of systems that require the ability for companies to remotely fix bugs, add new functionality, and patch security vulnerabilities. Unfortunately, remote software updating does not solve everything, and even creates its own set of security concerns because of added complexity. Bad actors may try to read the updates to steal or reverse engineer precious intellectual property, modify the updates to insert malicious code which could cause the device to malfunction, or update the system to install old versions of the software that have known vulnerabilities. In Beaverworks Summer Institute's Embedded Security and Hardware Hacking course, students are put through an exercise of designing and implementing a secure software update system, and then learning from their mistakes. After completing their systems, each team does a security evaluation on each other team's system to identify and exploit both traditional cyber vulnerabilities, as well as vulnerabilities that require physical or proximal access to the device. I hope that you are looking forward to the student presentations as much as I am. Hello, everybody. I'm Edward Krawczyk again. So I'm wearing a different shirt now, but now we're live with the students and we're going to start having students do their presentations. So like I said in the introduction, throughout this class, the students learn topics ranging from programming in Python and C to cryptography and all sorts of modern cryptographic algorithms, as well as programming embedded devices. And this all culminated in this capstone where they designed a secure bootloader to perform a firmware update for an automobile. And then after each team completed their designs, they did security evaluations on each other's designs in a capture the flag style event. So I'm incredibly proud of everybody here. They've done such an amazing job. We have 7 teams, and they've been very into this entire competition. They were working on it all day yesterday and some of them this morning as well, just outside of class in their free time. So without further ado, I want to start off by introducing the first team. This first team is called Metadata Attached.
All right. Hi, everyone. We're Team Metadata Attached, and our team consists of Oliver, Sakib, and me, Kitty. So to begin our presentation today, we would like to share an overview of our design for the firmware distribution system we have built. So first, we have the BL build tool here, which compiles the bootloader and generates the AES key, initial IV, and AAD, all of which are utilized later during the encryption process. In addition, the build tool also generates an HMAC key. Next, we have the firmware protect tool, which accepts the raw firmware, its prepended metadata, and its appended release message. The protect tool generates an HMAC signature of the entire blob and then encrypts the blob with a prepended HMAC. The encrypted blob and its attached authentication tag is then sent to the update tool afterwards, which receives the encrypted blob and constructs data frames for transmission. So first, a versioning frame is sent, followed by the setup, data, and finally auth tag frame. And then when the bootloader reads in the frames of data, it then checks the plaintext version and updates the AAD according to the incoming version number. Next, it receives the setup and data frames as well as the auth frame. If the red frames pass all of the previous checks, then a new IV is rolled as the decryption process begins. After decryption, the plaintext firmware is only installed if both the HMAC signature and version number in the metadata are verified. And with that, we conclude the overview of our system. All right, so this next slide provides a more elaborate outline of our frame or packet structure. So as you can see here, the first 2 bytes indicate the mode of the frame, which is followed by 6 bits representing the size of the data, which is then followed by up to 62 bytes of firmware blob data and a final empty byte. And from here, I'll be passing it off to Sakib, who will discuss more of the security features of our design system.
So here are our security features that we implemented. So the AES algorithm we use for encrypting our firmware is called AES GCM. Like other AES algorithms, its input consists of an AES key, initialization vector, and the plaintext. However, unlike other AES implementations, we also have the option of sending additional authenticated data, which can be useful when sending the version to our bootloader. This cipher returns a ciphertext and an authentication tag, providing both confidentiality and integrity. However, there is one glaring flaw in AES GCM, and that is the security of our entire system is compromised if we reuse IVs. As a result, we introduced a new system to make sure our IV is different for every time we use this algorithm. Next. So to combat the security flaw of reusing IVs in AES GCM, we devised a new system called rolling IVs. Ideally, we want communication between the update tool and bootloader to not include any sensitive information such as the IV. So we generate an initial IV for the bootloader and update tool and generate or roll a new IV using an incoming version. Since the bootloader and update tool have this initial IV, they will roll the same IV. This system makes sure we don't reuse IVs, thus keeping the security of our system intact. Next. To provide an additional layer of integrity, we use HMAC SHA-384. We chose SHA-384 because of its protection against collision and length extension attacks, and our HMAC algorithm is used to make sure that the bootloader knows for sure the firmware is coming from a legal update tool using our previously agreed on shared secret, which is the HMAC key.
And with those security features, we moved on into our attack phase. So our first attack was the rollback attack. The ciphertext included a unauthenticated and unencrypted metadata. So we were able to change the metadata of an old version to a new version and have it be accepted by the bootloader. Some possible remedies would be to authenticate or encrypt the metadata. Our next attack was the invalid firmware attack. Because there were separate blocks of CBC encryption, and there was no check on the ciphertext as a whole, nor as the plaintext on a whole, we were able to use the firmware version that we had upgraded to a newer version to have it be accepted by the bootloader. We were able to rearrange, delete, or duplicate blocks of data within that firmware to create a still valid firmware that would be accepted by the bootloader, but didn't contain the right plaintext when it was decrypted. Some possible remedies would be to encrypt the firmware all at once using CBC, authenticate the whole ciphertext or plaintext, or use an index to keep track of each block and how many blocks there should be. For our intellectual property tech, because the metadata again was unauthenticated, unencrypted, we were able to set the firmware size and the protected firmware to 0. The firmware size was never checked, and with setting the firmware, what it did do was set the start of the release message, which is printed whenever the bootloader boots. So by setting the firmware size to 0, we're basically saying that the release message started at the start of the firmware, meaning that when we booted, it would print out the firmware as the release message. Because it would stop printing out the firmware whenever it encountered a null byte or a byte with all zeros, we moved this firmware size, we increased firmware size every time to read it out past the null byte. So possible remedies would be to authenticate the metadata or check for discrepancies between the metadata for firmware size and the actual incoming firmware. For our malicious firmware attack, our first step was to break the CBC chunks into, they were packed as like 8 bytes of, 8 chunks of CBC, and we broke those each into chunks, into their own separate chunks with each with their own IV. What this meant was now we could control the IV for each separate chunk. And because the IV is XORed with the plain text or the output of the decryption algorithm before it's the plain text, we were then able to flip arbitrary bits in the plain text. By then using the plain text firmware that we had gotten from the intellectual property attack and finding the differences between that and the malicious firmware, we then XORed those differences with the IV for each corresponding block. That means we could send it to the bootloader, and when it decrypted, it would decrypt to the malicious firmware, which the bootloader would then store and run. Our final attack was the memory read attack. This is similar to our intellectual property attack. Again, we're setting firmware size to 0 to read out the initial firmware as the release message. And because the metadata is stored before the integrity of the firmware is checked, we're able to send that firmware size and then send an invalid firmware to fail the integrity check. The reason we do this is it's also necessary because even if we send no valid firmware, or if we send any valid firmware, it would erase the memory where the initial firmware is stored. So by failing the integrity check, we do not erase any memory. And then we read out the initial firmware as a release message and move it as we do in the actual property attack. Possible remedies would be to authenticate and encrypt the metadata, or to store the metadata only after checking the integrity of the firmware.
And lastly, we would like to conclude our presentation with some lessons we have gained through our BWSI experience. So the first two being teamwork and communication. These two aspects were especially essential throughout our design and attack phases because we constantly had to keep each other updated throughout that process. And during our design process, we also gradually grew to adopt the adversary or attacker mindset to identify existing vulnerabilities in our system to actually resolve them. And through the attack phase, we grew to better read and comprehend others' code, which in turn enabled us to sort of explore the interconnectedness of vulnerabilities in our attacks. And as Oliver mentioned, as one of our final attacks, we used a previously performed attack to actually progress with that particular one. And with that, we would like to end with a big thank you to everyone here. And we want to give special thanks to our instructors and TA.
Thank you guys so much. That was a great presentation. I want to first off say that your teamwork, I think, was really important for having such an effective attack phase. Like the first couple days, you guys just really rolled out a ton of attacks. So I want to ask you a quick question that came in over the live stream, which was, how did you generate new initialization vectors on the bootloader? What random number generator did you use? Anyone can feel free to answer.
Okay, so I found a couple of like really simple random number generators that are really effective for our means, and I tested them using a testing program to check if they're suitable for our use, and I eventually arrived on one. I don't recall the specific details of our PRNG, but yeah. So we use it to roll for every single bit in our IV. Byte in our IV. We use it to roll a new byte, and yeah.
No, that's awesome. Thank you. I'd love to ask more questions, but we're gonna move on to the next group. So thank you guys. Great job. Now we're gonna have Team ASI do their presentation.
Okay. Hello, we're Team ASI, and my name is Andreas.
I'm Lucia.
I'm Zach.
And Raiden is not with us today. He had a scheduling conflict. So, next slide.
So our goal for this design was to create a bootloader that will upload new firmware. And our design, it accepts only new, intact, and official firmware to protect our intellectual property. And the cryptographic functions we use are AES-128 in CBC mode for encryption and HMAC using SHA-256 for hashing. And we store all of those cryptographic keys in secrets.h, which cannot be viewed by attackers, but our firmware protect tool and the bootloader still have access to.
So what is AES 128? It's a symmetric cryptographic algorithm with a 128 key bit size and block size, and it uses the same key for encryption and decryption. We chose it because it's faster than AES 256 while still being secure, and it lets us share the key with the bootloader to decrypt firmware, and the keys are stored in secrets.h.
SHA-256 HMAC is a what we use for our hashing, and it's a cryptographic hash function, which is used for authentication of a message. And what we do is we would take a hash of the message we are sending and append it to the frame. And we chose it because it's used very efficiently to calculate a HMAC hash, and it's faster than other versions.
So this is just a basic overview of our design. So we've got our BL build tool, which makes the bootloader and our cryptographic keys. Then the bundle and protect tool, which protects the firmware. Our update tool sends the firmware to the bootloader. And then that's just an overview of the testing process, which will be gone over soon.
So our design, step 1, is setting up the frame of data. So our frame is made up of 32,768 entire bytes containing the hash, metadata, firmware, and the release message. We chose this number because it divides perfectly into 1024 size chunks, which can be easily programmed into Flash. After the frame is all set up, it's sent to SRAM. So step 2 is checking for authenticity. If the HMAC passes, then the data is decrypted using the same AES key because it's a symmetric algorithm, and a rollback check is performed. It's written to Flash, but if at any point validation fails, then the program will reboot and send ASCII art.
And for our design for the build tool, which we use to make our bootloader and compile it, pretty much all that it does is it compiles the bootloader and then generates a secret text file that contains our cryptographic keys. And our bootloader has several data checking methods, and it has keys that are used for decryption.
All right, so then this is our bundle and protect tool. And what it does is it takes in the firmware and then it adds zeros to the end until it's exactly 32,768 bytes. And we're doing that because that can, since we know it's going to be an exact time every time, that can prevent any extension attacks where people could add on extra stuff to the end. And then once it pads it, it'll encrypt it using AES and the keys from the secret text file. And then it makes a hash using that encrypted firmware, and it attaches that to the firmware blob.
And this is the update tool, which takes in the encrypted firmware from the protect tool and transfers it to the bootloader.
And for our testing process, this is how we validate the frames that we're getting sent from the update tool. And essentially, our entire system is based on checking an HMAC for authenticity. And since we check the HMAC of everything we receive, any modification to the firmware is immediately detected and we reset the program. But once the frame passes HMAC authenticity, we just decrypt the data, and then we check the version number and make sure there is not a rollback that the firmware updater is trying to do. And if all the tests pass, then we write the frames into Flash so the firmware can be booted.
So yeah, like Andreas mentioned, if any tests fail, it'll send out some ASCII art informing the user that something had gone wrong, and then it'll reboot. And then if all the tests pass, then it'll just load the frame into Flash so then it can be booted.
So after we were done with the defense, we moved on to the attacking phase. So we found a flaw in the way another team's bootloader printed the release message, since at the end of the frames, it would store the release message. So by switching the frames around, we were able to print their intellectual property and get their flags for points. In addition, because their metadata was unencrypted and not authenticated, we were able to change the version number and size, allowing us to upload outdated firmware.
And the 10 things we learned from our 4 weeks here were mainly how to program in Python, C, and as well as ARM assembly language. We also had a lot of experience using the Linux terminal. We learned a lot about how embedded devices work, as well as encryption algorithms. And finally, we had some experience using emulation software for running our emulated bootloader. And then we also learned a lot about common security vulnerabilities like buffer overflows and timing attacks. And we also learned about CPU architectures and how it relates to assembly language. And we also learned how to use GitHub and resolve merge conflicts when we are sharing and collaborating on our code. We also learned a lot about how to collaborate in a group setting, because we often had different ideas of how to fix or approach a problem. But what we would do is we would try to combine our different approaches to make sure everyone's ideas were being heard. And we also learned how to pace ourselves, because initially we kind of sped through our code and we got more done in a short amount of time than we expected. But we realized that we should slow down and check what we're actually creating to make sure it's secure. So we found a way to balance out getting code written and actually validating it and making sure there weren't any major flaws.
Right. And so just our overall Beaver work experience outside of class, we would hop on voice chat in our Discord server and we would just play a bunch of different games like Minecraft and Gartic Phone. And then in class, we got the chance to meet and collaborate with other students from all around the world. And it was an exciting opportunity to meet other kids our age with similar interests.
Yep, so thank you for listening. We really enjoyed the program. Thank you very much.
Thanks.
Thank you guys. You did a great job. I think Maddie's got a question for you, so I'll let her ask that.
Yeah, so again, congratulations team ASI, you guys did a great job. You were especially successful in the attack phase. So I was just wondering, what was the most difficult attack to pull off? Because I know you pulled out off about 5 or so, which is really impressive, by the way.
Just thinking the hardest attack probably was when we did it later, so it didn't make it into our slides, but we had to write a script so that we could open other teams' firmware binaries, and then we had to try and play around to figure out what bytes needed to be changed in order to try and get it to upload invalid firmware. So I think that was probably the hardest one we did.
Awesome, thanks.
Yeah. I think I'm just going to ask one quick question, which is, are there any aspects of sort of cybersecurity or just computer security in general that you were completely unaware of before you took this class? Did this, enlighten you to some new areas, or is it stuff that you've been familiar with?
Actually, I can answer this one. So personally, I was kind of surprised that time is a really big factor in cybersecurity. So no system is secure with enough time, and an attacker can break into any system. And it's kind of interesting how there are different approaches to limiting the possible values for like cryptographic keys based on how long it takes to compute an operation. And it's kind of interesting how balancing efficiency and security, usually in relation to time, is a big part of cybersecurity. So that kind of blew my mind in a way.
Well, thanks. And great job, guys. Wish we could, ask more questions, but we're going to move on to team error 707.
Hello, so I'm going to present our video. Hello, we are Error 707. My name is Rashita.
My name is Zui.
Is
My
this
name
sound
is
coming through?
Shreya.
My name is Minhaj.
In our project, we use 3 main encryption methods, and this is how they help. They're called AES 128, which is a symmetric block cipher. We use the same key to encrypt and decrypt, which helps ensure the confidentiality of the data, which is keeping the data private. We use SHA-256 hashing, which is necessary for RSA signing, which has a consistent signature algorithm for larger data. And this provides integrity, which is the accuracy and completeness of data. We use RSA signing, which is an asymmetric cipher, using the public key to decrypt and the private key to encrypt. Signature verification ensures the authentication of the data, or that the data is sent from us and not an outer party. Our design overview is this. We use 3 main Python tools and coded for a bootloader in C. First, in BL build, the encryption key files are created. The firmware is protected. The encryption methods using the keys we generated in build help protect our data. And later on, the protect firmware is sent to update, and update sends this to the bootloader to be uploaded or programmed into the flash. And then the bootloader can be then used to boot the updated firmware. And blbuild.py, this tool is responsible for the generation of encryption keys and the bootloader. First, we copy the initial firmware, and then the keys are generated, and then the bootloader is built. We generate the AES 128 key, the RSA private key, the RSA public key. Then we create the secret build output.txt, which is used by firmware protect to encrypt with AES and sign with the RSA private key. We also created secrets.h, which is used by the bootloader.c to verify and unsign with RSA public key and later decrypt in AES.
So our next tool is the FW Protect tool. This is where we secure the updated firmware and construct the firmware blob. Reading the keys from the secret build file, we create an AES 128 cipher. Then we encrypt the firmware with the AES 128 cipher, and then we construct the metadata, which contains our version, encrypted size, and unencrypted size. Now that we have the metadata, the IV that's generated as part of the cipher, and the encrypted firmware, we use the SHA-256 hash to hash them all together. Then we generate an RSA signature and we sign the hash. This is the final output would be the metadata plus the RSA signature, the IV from the AES-128, and the encrypted firmware, that's AES-128 encrypted, and the release message. Our next tool is the FW Update tool. So this is what's responsible for actually sending our updated firmware to the bootloader. First, we have to slice the firmware blob, which is the metadata, the signature, the IV, the encrypted firmware, and release message. So we first send the metadata as a whole, send the signature as a whole, and send the IV as a whole. However, with the slice, we have to slice the encrypted firmware and release messages into frames of their respective size of 18, and we send them individually to the bootloader.
This is the protocol for the update method in our bootloader, which is the program which runs as soon as the device is booted up, and it deals with any of the firmware inside the device. And the first step in the update protocol is reading in the version, which is the first 2 bytes of the metadata, then the encrypted firmware size, which is also 2 bytes, and the bootloader checks if the size is less than the limit of 30 kilobytes, and if it's divisible by 16, which is the block size of the AES in CBC mode. The bootloader also reads in the unencrypted firmware size from the metadata, which is also 2 bytes. It checks for version rollbacking, and then it programs to the flash the metadata, which is just the version and the unencrypted size. The bootloader then reads in the signed hash, which is 128 bytes, and then it continues to grab the RSA modulus and RSA public exponent from secrets.h to verify the signed hash and essentially unsign the hash itself. The bootloader then reads in the IV and also the encrypted data and the release message, which it reads in as chunks in frames of 16. It reads in the chunks size, which is 2 bytes, and then it reads in the chunk itself, which is 16, and it writes it to the data buffer. And this data buffer now contains the metadata, IV, and encrypted data again, which is then used to rehash in SHA-256, and then this newly hashed data is compared to the original hash, which was unsigned, and this verifies that it verifies the integrity of the data. Finally, now that we verified the integrity of the data, we decrypt this encrypted data with AES-128 by grabbing the AES-128 key from secrets.h, and we finally reprogram to the flash every 124 bytes of decrypted data, including the release message.
So far, we talked about our defense mechanisms. Now I will be talking about the attack phase. So during the attack phase, we focused mainly on finding the following flags: version rollback, invalid firmware, and malicious firmware. In these flags, what we needed to do was try to find vulnerabilities by loading an outdated version of the firmware. For example, if there was version 2, we had to try to run version 1 so we could get the flag. And we were able to run version 0 successfully. However, we did have some trouble with version 1 here and there. The next one was invalid firmware, where we tried to find vulnerabilities in the firmware integrity checking system by passing in our own firmware as version 2. Malicious firmware was somewhat similar in the sense that we were also testing for vulnerabilities in the firmware integrity checking system. And in this case, we tried to update existing firmware with the malicious firmware, which could be done if there is no authorized key on the update tool. Now for the reflections. So of everything we've learned, we decided to split it into a few categories: technical skills, soft skills, and miscellaneous. So as a part of technical skills, our entire group was able to expand on Python and C skills, especially with the applications of those languages in security, such as the implementation of AES, RSA, and hashing. Additionally, we learned about embedded systems, bootloaders, and how GitHub works, especially via the Linux terminal. Additionally, we also learned how tedious and painful debugging can be, but also how necessary it is to ensure that code functions as intended. In terms of soft skills, we learned that time management can be very challenging, and that with our group being from across the country, the distance can be rather hard to overcome, but once we were able to overcome that, it was actually a breeze. And miscellaneous has to do with that. We were essentially on a roller coaster over the past 4 weeks, as this was a challenging yet fun experience. However, it was really incredible to learn about all of the topics that we'd heard about before, but didn't really know how to actually implement. And it was also really great to meet new people with shared interests.
Thank you, guys. You did a really great job. I think Arthur would like to ask a question to you guys.
Yeah, so we have a question in the chat which asks, what was the hardest part of your protocol to write?
One of the toughest parts of our protocol to write was actually adapting the RSA to actually deal with the RSA keys, because at first we were confused about how they're supposed to be stored, and it took a while for us to actually learn that in Python the RSA key had to be exported. Well, the private key had to be exported so we can sign our data, but in Beaver SSL, which we use for our bootloader, our RSA key had to be split. Our RSA public key had to be split into its modulus and exponent.
Right. Thank you so much, guys. That's a great answer. And that's, yeah, I mean, that's great. I like that showed the learning process and learning the intricacies of an algorithm and how to, write stuff in different languages. So in the interest of time, we're going to move on to team group 4 now.
All right, I'm just going to share my screen real quick. And I think Jeffrey is starting us off.
Hello, we are team group 4, including Jeffrey, Hillary, Ian, and Kevin. And this is our presentation on our design project.
Okay, so the overview, first we have an authentication check, and then we send and receive metadata, and then we send and receive data packets until there's no more to send, and then it ends with firmware update, sending and receiving an empty data packet, and bootloader writing to flash.
One of the common algorithms that we used in our design was AES 128. Specifically, we used the CBC mode, which is the cipher blockchain mode. This is a symmetric block cipher, where symmetric means that the same key is used to encrypt and decrypt the data or plain text. AES 128 refers to the 128-bit key that is used. There's also an AES 256 variant, but we decided on using AES 128 because a 128-bit key would be very difficult to brute force anyways, and it was just faster and more efficient than the 256 kind. And we also used it because it was included in the Beaver SSL file, which is something the instructors made to make it a little bit easier to implement.
Yeah, so in addition to what Ian said about the AES 128, we also use SHA-256, which is a hashing algorithm. And so essentially what this does is it converts an input value and compresses it to a hash value. So this hash value, there are two to the 256 possible values for this. It essentially maps a larger input space to a much smaller input space. And so the reason why we're doing this is because this allows us to essentially authenticate or check whether or not the thing that's been hashed has been changed or not. And this is a good way to do this because an interesting property of SHA-256 is that if you change just a little bit on the input value, it has a huge effect on the hash value. And this was also in the Beaver SSL file, so it was quite convenient to use.
So the first part of our toolchain was bootloader build. And so the first step in that is generating a 256-byte random signature and 3 different 16-byte keys. And write that into our secret output.txt. And we write the SHA-256 hash of the signature as well as the keys into bootloader.c so that the C side has access to them. And we then build bootloader.c. And then we remove the added data that in step 3 from bootloader.c to prevent people from just reading it.
And the next up was the firmware protect tool. So what this would do is it would read in the signatures and keys from the secret output.txt file that we put the signature and keys in from the BL build. And what it would do then was it would encrypt the signature using one of the keys. It would choose, we generated 3 keys, so it would choose a random key out of those 3. So it would encrypt the signature using that key. And then it would create the metadata, and the metadata contained the version number, the size of the firmware, and the size of the release message. Then it would partition the data into chunks so that, because we sent out the data in frames, so not in just like one large thing. And then we would encrypt each chunk using another random key that we got from the secret output.txt file. And then we would write everything to the out file, which was the encrypted signature, the metadata, and the firmware and message.
All right, so once we've protected our firmware and everything we want to send, then we have the tool called firmware update. And essentially what this does is that it chunks up the data that we want to send into, like partitions it, and then we send over those chunks to the actual device, so the embedded system. And then we just do this process until we've sent over everything, and then it sends a null byte at the end to tell the device that it's finished sending.
One of the big security flaws that we had that allowed the attackers to get the rollback flag was that we did not encrypt our metadata, which is a huge oversight, and that just allowed us to that allowed the attackers to just change the version in the metadata and allowed them to boot old firmware. So that was a huge oversight by us.
More security flaws. So invalid firmware. Attackers were able to get invalid firmware by removing frames or swapping them around because we didn't encrypt the entire thing as a whole. So yeah. Intellectual property flag. Using the same tactic from invalid firmware, attackers could swap the chunk or frame that contains the release message with any other chunk that they wanted to read. And from that, instead of printing the release message, it would print out the desired chunk. That would give the attackers the intellectual property.
So even though we came across some security flaws, We also found ways to fix them. So for the rollback flag, we could have encrypted the metadata in the same way as the signature. So to prevent people from changing it. For the invalid firmware flag, we could have performed a hash of the entire message, including the signature and the metadata and a hash pepper, and sent that in after everything to prevent attackers from changing everything. For the intellectual property flag, we could have done the same solution as the invalid firmware flag.
As a whole, I think although our group may have had some big security flaws, I think through those flaws, we learned a lot about the cryptology concepts through our lectures, labs, and design challenge project. I think working through the issues we had in our initial design really made us learn more about cryptology than we did before. We also heard from researchers and professors from the seminars, and all of those were extremely interesting. And most importantly, we met and worked with our peers, who are all incredible high schoolers.
Yeah, and I just wanted to say thank you to everyone, and specifically to the instructors, Ed, Jake, Maddie, and then especially Arthur. So thank you, and I guess we can open it up to any questions.
And Jackie.
Yeah, and Jackie as well. My bad, Jackie.
Hi guys, thanks. Yeah, thank you. Actually, so great job. I think Jake's got a question he wants to read out to you. Does that sound right, Jake?
Yeah. So a lot of times it's easy to realize security vulnerabilities in your design after you've submitted, or even just after looking at other teams' designs once you're in the attack phase. So with all the vulnerabilities that you presented in your presentation about your own design, how would you have changed your design process now that you've been through it once to try to avoid having those vulnerabilities in future designs?
I think a big part that caused those issues to come up, and we didn't even think about that caused those issues to begin with, is we kind of focus really narrowly on one thing at a time rather than looking at the whole picture. We concentrated on protecting individual frames over like the security of the entire system as a whole. And I think in future endeavors, I guess we would sort of keep a broader view on things and remember to maybe not focus on one thing and get stuck in that for so long.
Thanks. No, that's a great answer. You know, part of security is, yeah, taking a step back and making sure that you're not focusing too much on specific details, but in the general case, your design is secure. So that's an awesome reflection. I think now we're gonna move on now to Team The Grass. And just a note for presenters, it might be best if your video is going to overlap with the graphics on your slide to turn your video off during your presentation portion.
Hello, our team is The Grass. I'm Jaden Pahukula.
I'm Tyson Yu.
I'm Jackson Pahukula.
And I'm Connie Chan.
All right, so for our overall design layout, this is kind of like a diagram of how all of our tools and things are all going to work together to secure our firmwares. So over here in our secure environment, we're going to start with the bootloader build tool, which all it's going to do is build the bootloader and like compile it and stuff. And then it's also going to generate the secret keys and the random IVs and things like that we're going to need later on down the line for encryption and verification and things like that. Afterwards, our bundle and protect tool is going to encrypt and package all the metadata with our firmware and package it all into one big bundle, which then will be sent out into the insecure environment where the hackers can see everything. And then the update tool will take that, program it onto the bootloader, which then the bootloader will decrypt it, verify it, things like that, and then it'll program it onto the flash. So first off, the build tool, this is probably the most simple out of them all. It's just gonna compile the bootloader and build it and program it onto our emulated microcontroller. Then after that, it will just it'll generate the random IVs and the random keys that will then be sent to the secret build output.txt, which other tools use later down the line to encrypt the firmware.
Next up, we have the bundle and protect tool. This tool will take the firmware from the firmware.bin file, and it will also take the HMAC and the HMAC SHA-256 key and AES key from the secret build output.txt from which was previously created. Next, we calculate the size of the firmware, which will help with the update tool and the bootloader tool later. We hash the firmware so that the hackers won't know what the firmware is. And if they, so we have the hashed firmware and the normal firmware, because the hashed firmware can't be undone. So we use the firmware. So in case that the firmware is hacked, we can compare the hashes of the hash firmware and the potentially hacked firmware, and then we can compare them to see if they are equal, and if they're not, then we can terminate. And then we encrypt the firmware and the hash as well as the release message, and then we pack the version, firmware size, encrypted blob size, and the encrypted blob, which involves like the encrypted firmware, HMAC, and release message, as well as the IV, which is used for the AES, and we put a null bit at the end to tell the reader when to stop reading.
So for crypto algorithms, we are using AES and CBC mode and HMAC as stated before, due to the simplicity in their implementation and because AES is reputable as the most secure globally and is the encryption standard for the US. Furthermore, we chose to use AES and CBC mode over ECB because with CBC, identical blocks do not have the same cipher, and the CBC encryption can be used to encrypt larger messages. We chose HMAC to get another layer of security, and because the 256-bit key is sufficiently long enough for preventing third parties from being able to brute force the hash values and identify their original values. So for our update tool, we took the encrypted data from the firmware bundle and protect tool and divided it into frames. Then we sent that data out with the frame size to the bootloader, which will then decrypt it.
So for the bootloader is first going to read in frames from the firmware update tool and check the hashes that it put on the frames to check integrity and make sure that none of the frames are tampered with. Then it puts all the frames back together and checks the HMAC to just another layer of security to check the authenticity of the firmware. And if it's good, then it'll decrypt the firmware using the key in secret build output.txt. And then it saves and checks the hashes of old versions to defend against duplicate firmware being uploaded. Some weaknesses in our system is that we're vulnerable to less common and more complex attacks like differential power analysis and other high-level attacks. When we design our system, we took into account who would be attacking our system and also weighed in the simplicity of implementation. And so we were able to determine a certain amount of security that we wanted to implement. And then, of course, there's going to be other weaknesses that we don't know about that hopefully we'll be able to find by improving our design. Thank you.
All right, any questions?
Great job, guys. That was a great presentation. So I guess a question is, so you said there were some weaknesses that you don't know about, right? And that's kind of the thing when you don't have a comprehensive security audit on your designs, stuff you don't catch. Were there any weaknesses that you heard about in other teams that you think may have applied to yours?
actually, sorry, yeah, actually, I think there is. I think it was gonna be Air 707 or maybe one of the other earlier groups that we heard. Actually, just now we kind of were talking about how our metadata wasn't encrypted either, so it wasn't encrypted either, so people could have changed that to use to do some sort of like attack where they could give us an older, more vulnerable firmware instead of a newer, updated one. So that's something that we could fix in the future.
All right, thank you. Yeah, no, it's great to hear you guys reflecting on stuff afterwards.
Yeah, thanks.
So great job. We're gonna move on to Struck by Lightning now.
Okay, hi everyone. Welcome to our design and attack presentation. My name is Lauren.
My name is Sol, and I'm Marco.
Sydney's not able to be with us today, but here is a group photo of the four of us. Our name is Struck by Lightning, and we're gonna go ahead and begin with an overview of our design.
So in Pink, you can see all the files that we made. Everything starts in VL build, which creates random keys and sends them off to the bootloader and the firmware protect tool. Firmware protect secures the firmware with encryption and hashes and adds metadata to the firmware and frames. Firmware update splits the entire blob and sends the frames to the bootloader. The bootloader makes sure everything is okay and then installs them.
Okay, so here's a security overview. Our main strategy was to encrypt the entire firmware in one go, and then we'd create metadata from that, send that along with hash, and then we'd loop around with the encrypted firmware and send that with the metadata and hashes, and we'd hash the entire encrypted data and then send the release message along with the hash, and then we created something called a Big Mac, which is a hash of the entire encrypted firmware data, the metadata, and the release message. And then we'd send the IVN tag. So our strategy was really HMAC reliant, and we checked integrity and authenticity many times to ensure that nothing was changed. And we only did one AES because it doesn't require heavy encryption. And this is just a diagram of our frame structure, which is looped and sent over to the bootloader.
So with our frame structure, we used two main algorithms. So the first one was AES 128 GCM, and this allowed us to provide encryption and confidentiality on our firmware. So this is a symmetric block cipher, which uses a key initialization vector and a plain text. The reason we chose it is it was very fast and it provided authentication. So we were able to double check that nothing was changed or exploited during the transferization process of our frames. The second one that we used was HMAC SHA-256. And we used this as
We're losing Lauren's sound. Can somebody fill in?
Can someone hear me?
Hey, Lauren, you're cutting out a little bit.
Oh no.
We can hear you now though.
Oh, you can hear me now? Okay. I'll just go ahead and restart with HMAC again. So the second one that we used was HMAC SHA-256 as a hashing algorithm, and this allowed us to provide verification along with integrity and authenticity checks. We make sure that our packets were not changed or exploited, and we use this a lot throughout our data frames, so our individual data packets, along with the Big Macs that we sent to make sure that packets were not able to be rearranged or then change themselves.
So throughout the process, we added extra visuals like 3D spinning animations, ASCII art, different colors, and progress bars into our Python tools. And on the next slide, there's an example GIF of what it would look like. So we have our progress bar, and then our spinning lightning bolt because we're struck by lightning. Okay, so an example attack we defended against was version rollback. So we wouldn't want attackers to be able to access a version older than the current version. So what we did was we packed the version into the metadata, and in every single frame, and we hash that. So we would be sure that if the version number was changed at any point, the program would be able to detect that.
Another attack that we defended against was an integrity attack, which allowed teams to switch the order of our data frames to exploit the transfer of packet data. So we used a lot of HMAC for our frames and our metadata to ensure that these were not tampered or exploited. So what we did was we HMAC'd individual frames along with the entirety of our data packet sent, so that we made sure that the data of our individual frames were not tampered with, and then our frames were not switched around inside of our Big Macs or our entirety of our data packet sent.
Another attack that we defended against was a buffer overflow attack. So overflowing the bounds of a variable allows someone to override memory and change how a program runs. To combat this, we added bounds checks and hard limits to all variables that were read in, and also for all for loops. This can be a big vulnerability if it is not defended against, since attacks can gain a lot of control.
So throughout the process, we created extensive documentation. So we created a separate documentation PDF, which outlines our process, explanations of our different functions, our attack process, and a summary. And this ended up being 13 pages long. And we also wrote extensive comments in our code to make sure that we had security by security and not security by obscurity.
All right, so the attack phase. We first prepared by looking for mistakes that people could have made that we had thought of for our own design. Things like version checks, integrity and authenticity of firmware, and bounds checks. So our first attack was changing metadata. One team had no integrity or authenticity checks for their metadata. This allowed us to change the size and version of their firmware. A version rollback is when a version is installed that shouldn't be, which is any version that is before the current one. We were able to change the version from 1 to 0 in the firmware file, and it installed and we got the flag. We used the same method to get the intellectual property flag, which is being able to read data within the protected firmware. The release message was determined by the size, and we could easily change that. This exploit allowed us to output many parts of the memory very easily. Our second attack, we were also able to switch the frames in the firmware. The team didn't check the order of the received frames and allowed us to change that order. They could have used encryption or had a hash of the entire firmware to prevent this, since they would be able to find the difference between the two. Our third and most complicated attack was a buffer overflow. Using it, we changed the release message address. When the firmware boots, the release message is outputted so we could output most of their memory. The only issue was that it would stop at a null character, so it took a lot of trial and error to get what we wanted. We also could change the link register, which is the return address of a function. And it's possible to point that address back to the address of our read-in buffer and have shellcode there. With that, we would have complete control over their bootloader.
So now a reflection. So we learned a lot of valuable lessons, such as the value of taking breaks and giving our brain a rest. The second one that we learned is a very concrete plan. So in our beginning stages of our design process, we created like a 10-page document outlining all the code we wanted to implement, along with the attacks that we wanted to prevent against, and then attacks we wanted to do in the future. So a plan was a very good way of going about our design process. The third one that we learned about was teamwork, being able to work together to split up writing the code, writing documentation, and working together to create our design. And then some future improvements. So since we were virtual, we weren't able to use a physical hardware device such as a Stellaris. So in the future, we need to consider physical hardware attacks such as side channel attacks. The second improvement we would make is practice using attack methods and to further our knowledge of various attacks. We wish we had more time to learn about attacks and then perform them as well. And then the third one is implement RSA signing. In our original design, we wanted to implement RSA, but we did not have enough time to perform this. So in the future, we would improve on those things. So thank you so much for listening to our presentation, and thank you so much to all of the instructors. You were incredible, and thank you so much.
Thank you, guys. You did a great job. Also, that was a really nice presentation. We actually have a question from Kevin. I can ask it for him. He put it in the chat. He says, do you think the amount of HMACing you did is overkill, and do you think it created a speed bottleneck?
So we did do a lot of HMACing. I don't think we needed to do that many because, in fact, maybe even the Big Mac at the very end, maybe that by itself was enough to check integrity. But I don't think it created a speed bottleneck because when we tried attacking the other teams, our program actually seemed quite fast in comparison to other teams, even though we HMAC'd a lot.
Thank you. That's great. No, that's also cool. There was another question that Arthur was going to ask about how you defend against buffer overflows, but you answered that, so that's great. So wonderful job. In the interest of time, we're going to move on to error 404. And if I'm recalling correctly, you guys might have a video. So if you're going to do that, just make sure you turn your cameras off.
We don't have a video. I'll just share my screen. Okay, that's my bad, sorry. So we're arrow 4, brain not found. All right, my name's Emith.
Oh, my name's Farhan.
I'm Michael.
I'm Tejas.
Here's a general overview of our design for the embedded system we created. It all begins at BL build, where we create AES and HMAC keys, which are sent to the bootloader and the firmware protect file. We then move on to firmware protect, where we encrypt the firmware using AES, which is then sent to firmware update. In firmware update, we construct a message made up of multiple components, and we send that to bootloader. And in the bootloader, we perform a process where we check the metadata and make sure it conforms to our requirements. And after that, we send it to update based on what the outcome is. And we will go into more in-depth descriptions of this in the next slide.
So BL build is a Python file that compiles bootloader.c, but it also generates the AES key, the IV, and the HMAC key, all of which are necessary for security algorithms. It then sends these keys to two different files, secrets.h and secret build output. They both serve similar purposes, with bootloader.c reading from secrets.h, while firmware protect reads the keys from secret build output.
All right, so our next file that we have in, I guess, Streamline is FW protect. So this is doing a bunch of things. So the function, first of all, accepts 4 parameters: in file, out file, version, and release message. The in file being the unencrypted firmware data, the out file being where FW protect writes to, version being obviously the version number, and release message being the release message. So it first reads its keys from secret build output generated by build and the firmware from the in file. It then generates an HMAC between the provided key and the firmware data. It creates a firmware blob variable, which consists of the firmware and the HMACs that are sort of appended next to each other. I'll elaborate more on why we use HMAC later on. We add null bytes because of how we're using AES 128 in CBC mode. So obviously, in order to do that encryption, your data needs to be multiple of 16. So that's the reason we have null bytes there. So we encrypt both of those. And finally, we pack the version, firmware size, null byte count, and release message size in little Indian shorts. This is so that our bootloader code could work better later on. And finally, we attach all of this data together in the appropriate format and write it to the out file. So yeah.
Firmware update is the file that's doing most of the work when it comes to sending the data to the bootloader. So what we did is we had a frame length in 2 bytes. So the bootloader would take that in and realize that there's X amount of bytes that are going to come in, and then it'll read those next bytes, which is going to be the data. And then the bootloader would send an OK message to the firmware update file, which would kind of act as the go ahead message, which meant firmware update can send another file. And then that would go back and forth until the last file is sent. And the data is essentially everything from firmware protect, which includes anything that the bootloader might use, such as the size of the data, the version, the HMAC, the firmware message, and the data itself. So we implemented a few strategies to make sure that there would be integrity and that we can check the validity of the incoming firmware. So the first thing we did is, in order to avoid overflow attack, we counted how large the size of the data was going to be. So if it exceeded 30,000, then we would just simply reject it. If the HMAC was different from the file than what we actually calculated in the bootloader, then we would reject it again, and that would make sure that the data was untampered. And we also compared the version number to the version number that we stored in the bootloader to make sure that rollback attacks can be implemented.
All right, so for our security algorithms, so we use two, I guess, primary security algorithms in a sense. One of them, AES 128 in CBC mode. There are multiple reasons for this. The first reason, there's a pre-provided library, Beaver SSL.h, which means that we actually already have AES 128 CBC mode functions to use for decrypting in C. We opted for this because, we're going to be honest, we struggled a bit with like sort of writing our own security algorithms, and because these functions were pre-provided, we were confident that they would work. We also decided that 128-bit encryption, it was sufficient for our needs. We didn't really need anything more secure, because that would actually add on to time complexity, and we just didn't really need that. And finally, CBC mode, it allows for the use of an IV, which adds like a certain level of randomness, which makes it really difficult or practically impossible, as a matter of fact, to predict the encryption algorithm. We also use HMAC and SHA 256, SHA-256 configuration. The reason we use this is because it's very similar to AES. It just works. The only clear vulnerability on the map is at UART1. So that's the reason we use an HMAC. We could test firmware before and after it travels through UART1, and we could test for validity that way. And if HMACs don't line up, then we know that something was modified. Okay, so for our attack phase, one vulnerability that we discovered, it had to do with a group who didn't have their home firmware hashed. I believe that's a typo, sorry about that. Because of this, it would have been possible to implant our own firmware, which would have netted us the invalid firmware flag. All right, so for things that we learned how to use GitHub in a collaborative setting. We also gained a tremendous amount of understanding about the technicalities in embedded security. So like when we were programming, there were like a lot of nuances and just things we didn't really think of first that we sort of had to account for. We learned how to optimize for C. So we learned how to write code for C. And finally, we learned that communication is super important, because if we were communicating, I feel like we might have worked a bit more efficiently, and yeah. All right, so thank you for the instructors. You guys were great. Thank you for BWSI admins for setting this whole thing up. Thank you, everyone.
Thank you. Great presentation. I really like, how you talked about teamwork. Do you feel like, so I think you had a really effective team. Going back, do you think if you were to do another CTF, maybe it were a different challenge, that you'd be, a lot more prepared, just based on, not just based on the knowledge, but, knowing how to split things up and split tasks between different members of your group?
Absolutely. I feel like one problem that we had with this is that we sort of had to like learn the content while we were doing it. And then in the future, we would maybe know how to like distribute tasks, because we know like what tasks need to be done to create like a proper bootloader. So I feel like in the future, with our current knowledge, we could create a far more effective bootloader, like a more security system.
Great, no, awesome answer, thank you. So that's actually been all of our group presentations. And I want to sort of tag off of what he was just saying there, which is, the students were learning the material as they were doing this, and the material they were learning, a lot of it's college level. It's nothing that like I ever had access to in high school. It's incredibly difficult. And I can't stress enough how impressive it is that all of these students, not only completed the class, but grasped everything and understood everything enough to be able to do this project. And then particularly to be able to, go and pull off attacks. So this is truly like, everyone has done an amazing job. We want to thank all the students for being enthusiastic and working hard, especially on a virtual environment. I also want to thank my co-instructors. So let me make sure I get everybody. Jackie Zimakakis, Jake Greisel, Arthur Zhang, and Maddie Esty. We couldn't have done it without you. And I also want to say one final thank you here to Tom from MIT Media for helping us with this live stream. With that, I believe that we've concluded all of our presentations. We can open up the floor to any questions that anyone has just about the experience in general too.
Yeah, I have a general question for the students, actually. I asked a similar thing last year. I thought it was interesting. After taking the class, do you have like a different outlook on technology? I don't expect you to have one, but has your outlook on technology and security and the internet and electronics changed at all? Do you think differently about the technical world now, or?
I guess I could speak about that. So yeah, so this class, it sort of made me maybe a bit more afraid in a sense, because when you think about like cracking like some huge algorithm or like some huge system, you don't really think about how you would do that, assuming you don't actually know anything about cracking systems. And I feel like this class, because it like showed how cracking systems like that is possible, it makes me maybe a bit more afraid and skeptical of all the systems that we have in place right now. So yeah.
There's a great answer. One of the students said, "I will never look at hacking in movies the same way ever again." I appreciate that. Okay, now there's sort of one more answer, which it was intended in sort of a joking manner, but I'm going to interpret it in a more serious manner for the live stream, which is basically a student saying that you shouldn't write your own cryptographic code, and that's exactly right. So that's sort of the saying is don't roll your own crypto and don't implement your own crypto. So it's great to hear that people have learned that. And so the reason for that is sort of the exercise we've covered in this course is that everybody, when you write code, you make bugs, and bugs are exploitable. And it's not even a problem with stuff that you write. Maybe it's the hardware that you're running on has some problems with it that are exploitable. So yeah, knowing what you should write in a system and what you should leave up to someone who's like a certified expert in the field to write, that's a great point. Okay, so we have 1 minute left in the live stream. I'm just gonna sort of sit here and see if any questions come in. If not, thank you everyone, and great job.